Hi everyone, in this video I want to talk about threads and concurrency. So why we are curious about threads? There are several reasons for that, but I want to discuss them with an example. So think about Microsoft Word application. Whenever you type character, Microsoft Word should at first display that character and simultaneously check your term for probable spelling mistakes and simultaneously check your whole text for grammatical mistakes. So for these reasons, we should use multi-thread in several applications like Microsoft Word. But the question is why we just don't simply use processes in these situations. So the answer is process creation is heavy weighted and it's very slow and it demands lots of memory space. So we prefer to use threads in lots of situations. And another reason is that the matter of programming. Creating a process is way more harder than creating a thread. So lots of time we just prefer to write a multi-threaded application. And another reason is that most of the kernels handle multi-thread applications. So let's look closer to the single thread process and multi-thread process. In a single thread process, as we know probably, a process has code, data, files, and the registers, which are the variable inside our CPU, PC, which is a variable that shows where we are in code, and stack which is the stack memory of our program, actually our process, and a single thread. But in contrast, in multi-thread process, we have same code, data, and files, but for each process we have several threads, and each thread has its registers, a stack, and PC. So all of the threads use same code, same data, same files, but each of them has different registers and different stack and different PC. So as we could see here, if we want to make several processes, we should copy our code, our data, and our files. So which is a redundant data. So in this slide we could see one of its process. So, and if we want to think about a simple server architecture, actually multi-thread server architecture, whenever a client send a request to server, and server receive that request, server will create a new thread to service that request, and another thread still checking for new requests that other clients could probably send in few seconds, in the next moments. Yeah. So again, if you want to recap the benefits of a multi-thread application, we could mention its responsiveness, because so if our application have only one thread, then the problem is that when our application want to do something, every other part of our application will be freezed. For example, if you are, for example, imagine the situation that you are compiling a code in your computer. You probably don't want to You probably want to use other part of your computer, for example, your cursor. So yeah, so in user interface, it is essential to have multi-thread application. And in resource sharing, which we covered in the previous slides, and again, creating a new process is more expensive than creating a thread. So if my computer has several core, multi-threaded application could take advantage of all of those cores, but it will put pressure on programmers because lots of difficulties arrive. For example, programmers should think about balance. For example, all threads should probably have same difficulties for our computer, and data splitting is one of the another challenge, and data dependency. For example, if one thread changed the same data that another thread are using, it will probably make some difficulties or maybe some bugs. So, and debugging these applications are very hard, and because in single thread application you could simply just track your code and see your and see how your code are behave. But in multiple thread, if you run your code several times, your application probably behave in several your application probably behave differently. So it's very hard to debug these applications. But the advantage of multi-thread in multi-core situation is that it could use parallelism. It means that your program could do more than one task simultaneously. So imagine that your application has 4 threads, which in this image we mentioned those threads by T1, T2, T3, and T4. And if your computer has only one core, then the CPU will be switched between threads. For example, from thread 1 to thread 2, from thread 2 to thread 3, and again from thread 3 to thread 4, and again from thread 4 to thread 1, and goes on and on. But if your computer has several core, for example 2 core, your computer could run thread 1 and thread 3 in core 1 and thread 2 and thread 4 in core 2, which is speed up your program by a factor of 2, which is impressive. We have 2 types of data parallelism. We have actually two types of parallelism. One is data parallelism and another one is data parallelism. So what is the difference between these 2 kinds of parallelism? So in data parallelism, you will divide your data into several parts, and each thread work on one part, actually one core. Each of your threads should be allocated to one core, and so if each of your threads allocate to one part of your data, it means that one core is working on one part of your data. So it's data parallelism. But in task parallelism, each core work on the whole data, but they have different purpose. So let's think about this example. So think that you have an image and you want to find, for example, dog in that image. One way to do that is to make 4 threads and divide your image into 4 parts, and each thread search for dog in its allocated part. For example, thread T1 search for the dog in the upper left part of the image. So it is an example of data parallelism. But in task parallelism, imagine that you have an image and you want to find all dogs, all cats, all birds, and all tree, for example. Yeah. So you could make 4 threads, and for example, thread 1 search for dogs in the whole image, and thread 2 search for all cats in the whole image, and thread 3 for birds, and thread 4 for tree. And so this is an example of task parallelism. But the question is how much we could take advantage of multiple cores. Amdahl's law says that maximum theoretical speed up is limited by that blue formula. In this formula, n is the processing cores and S is serial portion. So let me clarify S with an example. So imagine you have an application that takes 4 hours to run completely, and 1 hour of that application couldn't be parallelized. So yeah, 3 hours of that application could be parallelized, but 1 hour of that application couldn't. So in this case, S is 1/4 because 1 hour couldn't parallelize. It is actually the ratio of serial portion to the whole task. So this is our limitation. So this is an example. If we have several cores, which we could see on x-axis is the number of cores that we have, and on the y-axis we could see the speed up ratio. And so ideal speed up is that if we have, for example, 10 cores, our speed up it is ideal for our speed up to be equal to 10, because we have 10 core. But in reality, we couldn't reach that goal, because lots of applications have limits. For example, if S is equal to half, so you could see that we couldn't actually reach higher rate by adding more cores. So how our operating system handle multiple threads? There are several ways to do that, but but the point is we have several user threads which are user built, and several kernel threads which are operating system C. But what is the difference between these two kind of threads? So if in some language, for example in Java, you build several threads, it is probable that your compiler didn't make exactly the same number of threads in kernel space. maybe it will merge some of your threads, and those threads act like a single thread in kernel space. But how these threads match? There are three main ways to do that. First one is many-to-one, second one is one-to-one, which is commonly used in our systems, and the last one is many-to-many. So let's discuss these kind of multi-threading models one by one. The first one is many-to-one. So we built several threads, and our computer thread them as a single thread. So yeah, this is one way, but it is not commonly used nowadays. So let's go to the next model. One-to-one. This is commonly used in our systems. So whenever you make a thread when you add a thread in user space, your operating system will treat that thread as a kernel space. In kernel space as a single thread. So the number of user threads is equal to the number of kernel threads. And Windows and Linux use this kind of handling multiple thread. Another way is many-to-many model. It is a bit difficult for operating systems, but in theoretical point of view, you make several threads, and these threads are run by several other threads in kernel space. Yeah, but as I told before, it is not very common. And two-level model is somehow mixture of the second and third way. So you have several one-to-one threads and several many-to-many threads. And that was it. Thank you for watching us.